Okay, we have another integral today from the MIT Integration Bee 2017, number 16. We have the integral from minus infinity to infinity, sine squared x plus pi over 4 over e to the x squared dx. Okay, I think this was a pretty unique problem. I don't think I've done one quite like this before. The first thing I notice is that we've got e to the x squared in the denominator. We've got these infinite bounds. If I just bring this into the numerator, this becomes e to the minus x squared. And it's starting to look a lot like the Gaussian integral. That part is exactly the Gaussian integral, except we've got to deal with this part right here. But now for sine x plus pi over 4, I can just use the angle sum formula for sine. So I can write this as, we can break this up as sine x times cosine of the second part, which is pi over 4, plus sine of the pi over 4, just reversing the order, and then we'll have cosine x. But both of these values are the same. It's 1 over square root of 2. So what I can do is I can kind of just factor the 1 over square root of 2 in front and write it as sine x plus cos x. But now this whole thing is squared, right? So we can square it here, square this, and square this. And then what's going to happen when we square this, this just becomes 1/2. This here, we'll just multiply it out. We're going to get a sine squared x plus cosine squared x. And the middle terms become 2 sine x cos x. But then this right here is just going to be a 1. This right here, we can use double angle formula and write it as sine 2x. So just making it clear, what we have here is half 1 plus sine 2x. I think what I'll do is we'll take this, put this back in the integral, and continue from there. Okay, now we have it rewritten with the 1/2 out front as a constant, e to the x squared into the numerator. Next, what I want to do is, if I just distribute this e to the minus x squared in here, we can split this up into two integrals, because for the first one, we're just multiplying by 1, so we're going to get the Gaussian integral, and then we can deal with this one after that. So now we have our Gaussian integral right here, so we know the value for this is going to be just square root of pi. Multiply in this 1/2, and of course this is going to be square root of pi over 2. Coming over here to deal with this second integral, if we just look at this right here, the thing is, if we call this whole thing f of x, and we try to evaluate f of minus x, plugging in minus x everywhere here, we're going to have sine minus 2x. On the x squared, it's not going to matter, right? The minus sign is just going to get squared, and it's going to go away, so this is going to become e minus x squared, same thing. Then here we can take the minus sign out front, because sine is an odd function, and write it as minus sine 2x e minus x squared. But this right here, this is going to be the same thing, because this is f of x, this is going to be minus f of x. And if f of minus x equals minus f of x, then we can say that this whole thing right here is an odd function. When we have an odd function, we're integrating an odd function, and our bounds are symmetric around 0, we can say the whole thing is going to be equal to 0. This whole thing becomes a 0. And so just focusing on this one over here, for my final solution of this, we have square root of pi over 2. Okay, there you go. Another good one from MIT 2017. Thanks everyone for watching. Have a good day.